In the middle of our galaxy, there's this incredibly heavy thing that's like 4 million times bigger than the sun. It's so heavy that it warps space and time around it. Light can't even get out if it gets too close. We call it Sagittarius A, and it's basically a supermassive black hole. Black holes form where big stars used to be in the middle of galaxies, and where our knowledge ends. They're natural, made by gravity, when too much stuff collapses into a small space. Even though we expect them, our rules can't completely explain them. Scientists spend their lives searching for puzzles, doing tests to find things that don't fit our rules. What's cool about finding more and more black holes in the sky is that each one is like a test nature did that we can't figure out yet. It shows there's something important we're missing. In this video, we're about to take a thrilling dive into the enigmatic world of black holes. The study of black holes began in 1915 with Einstein's general theory of relativity. This theory made two bold predictions. First, that massive stars collapse to form black holes with a singularity at their core, and second, that there's a singularity in our past, marking the universe's beginning. This insight is found in a famous 1973 textbook by Stephen Hawking and George Ellis, introducing terms like black hole and singularity into common language. It explains that when massive stars die, they collapse under gravity, leaving behind a mark on the universe's fabric. But beyond a certain point, there's a singularity, a moment where our understanding of nature fails. According to general relativity, this singularity marks the end of time. Additionally, there exists a singularity too in our historical timeline, signifying the commencement of time, the Big Bang. We are prompted to embrace the profound concept that our scientific understanding of gravity, the force governing the motion of planets and moons, fundamentally revolves around the essence of space and time. It might not seem at first that gravity has anything to do with space and time, or that trying to explain it scientifically could make us think about the start and end of time. But black holes play a major role in uncovering this connection because they represent gravity's most extreme forms that we can observe. Black holes were such a puzzle that even until the 1960s, lots of physicists thought that while they might show up in the equations of general relativity, the universe would somehow avoid making them. Einstein himself, back in 1939, wrote a paper saying that black holes don't exist in the real world. Another famous physicist of his time, Abe R. Reddington, summed it up more simply. There ought to be a law of nature to stop a star from acting so strangely, but actually there isn't, and they do. We've come to realize that black holes are just a natural part of what happens to stars that are a few times bigger than our sun. And since there are millions of stars like that in our galaxy, there are also millions of black holes. Stars are basically big bundles of stuff trying not to collapse under their own gravity. In the beginning, they fight this collapse by turning high hydrogen into helium deep inside their cores. This process, called nuclear fusion, generates energy that counteracts the collapse. Right now, our sun is in this phase, converting 600 million tons of hydrogen into helium every second. It's easy to overlook such enormous numbers in astronomy, but it's worth pausing to contemplate the staggering difference in scale between stars and our everyday experiences. 600 million tons equates to the mass of a small mountain, and our sun has been steadily consuming this amount of hydrogen every second since before the Earth formed. But no need to fret. It still has enough hydrogen to keep defying gravity for another 5 billion years. The sun manages this feat because of its immense size. It could fit about 1 million Earths inside it comfortably. The sun, with a diameter of 1.4 million kilometers, dwarfs a passenger jet, which would need 6 months to circle it. However, in astronomical terms, the sun is relatively small. The largest known stars are about 1,000 times bigger, stretching the diameters of around 1 billion kilometers. If one of these behemoths were placed at the center of our solar system, it would swallow Jupiter whole. These colossal stars will ultimately meet their end in a cataclysmic collapse under their own gravity. Gravity is a subtle yet relentless force. Its nature is purely attractive, and in the absence of any strong or opposing forces, it acts endlessly, Gravity endeavors to draw us downward toward the Earth's center, and it exerts the same pull on the ground beneath us. The prevention of everything collapsing into a single point lies in the rigidity of matter. It consists of particles governed by the laws of quantum physics, which repel each other when brought too close. However, this apparent solidity of matter can be deceiving. We often overlook the fact that the ground beneath our feet is predominantly empty space. The swirling electron clouds encircling atomic nuclei maintain separation between atoms, creating the illusion of densely packed solid objects. However, the truth is that atomic nuclei occupy only a minuscule portion of an atom's volume, rendering the ground beneath us as insubstantial as vapor. Despite this, the internal repulsive forces within matter are formidable enough to prevent us from plummeting to the floor and to stabilize dying stars up to twice the mass of the sun. Nevertheless, there exists a threshold, and this threshold is examined by neutron stars. A typical neutron star boasts a radius spanning just a few kilometers, yet its mass equals approximately 1.5 times that of the sun. Imagine 1 million Earths compressed into a space no larger than a city. Neutron stars often exhibit rapid spins, emitting intense beams of radio waves that resemble a cosmic lighthouse illuminating the universe. The initial detection of such a neutron star, known as a pulsar, dates back to 1967 when Jocelyn B. Burnell and Anthony Hewish made the groundbreaking observation. The pulsar's pulsation is so precise, occurring every 1.3373 seconds, that Burnell and Hewish humorously dubbed it Little Green Men. One of the fastest known pulsars to date, PSR J 1748-2446 AD, spins 716 times per second. Neutron stars represent highly energetic celestial entities. A notable event occurred on December 27, 2004, when a burst of energy struck Earth, temporarily blinding satellites and causing our ionosphere to expand. This surge originated from the rearrangement of the magnetic field surrounding a neutron star positioned 50,000 light-years away on the far side of the galaxy. In just a fifth of a second, the star discharged more energy than our sun emits in 250,000 years. The gravitational force experienced at the surface of a neutron star is a staggering 100 billion times stronger than that on Earth. Any object falling onto its surface is immediately crushed and morphed into a dense soup of nucleons. If you were to descend onto a neutron star's surface, the atoms constituting your body would disintegrate, transforming into tightly packed neutrons vibrating at nearly the speed of light in a frantic attempt to avoid each other. This vibration can sustain a neutron star weighing approximately twice the mass of our sun, but surpassing this threshold spells defeat for gravity. Should additional mass be added, the sized star would collapse, birthing a space-time singularity. Some scientists liken the singularity at the genesis of our universe, the Big Bang, to a day devoid of a yesterday. Similarly, a singularity arising from gravitational collapse marks a moment bereft of a future. What endures beyond is a somber remnant of former brilliance, a black hole. Concrete observational evidence now confirms the widespread presence of black holes within our universe. These images, acquired through the collaboration of the Event Horizon Telescope, an array of radio telescopes spanning the Americas, Europe, the Pacific, Greenland, and Antarctica, provide a compelling glimpse into cosmic phenomena. Among these visuals, the left-hand side image unveils the central supermassive black hole residing within the M87 galaxy, positioned 50 million light-years distant from Earth. This colossal black hole, with a mass 6.5 billion times that of our Sun, occupies the central void within the image, recognized as a shadow. The darkness enveloping this region arises from the immense gravitational force impeding the escape of light particles. A fundamental law of nature nested within this shadow lies the event horizon of the M87 black hole, a vast sphere in space spanning 240 times the distance between Earth and the Sun, serving as a protective barrier separating the external universe from the enigmatic singularity within. Surrounding this shadow, a radiant disk forms, predominantly composed of light, rays emitted by swirling gases, and dust converging into the black hole. Their trajectories are contorted into a distinctive Dutch shape by the gravitational influence exerted by the hole. On the right-hand side of the image lies the supermassive black hole residing at the heart of our own galaxy, Sagittarius A. Despite its astronomical significance, it weighs a mere 4.31 million times that of our Sun, rendering it relatively diminutive. The luminous disk surrounding it could easily fit within the orbit of Mercury. Its existence was initially deduced indirectly through the observation of stellar orbits around it, particularly the S stars. Among these stars, S2 orbits in close proximity to the black hole, completing a cycle every 16 years. The precision of these orbital observations proved vital as they were compared with the predictions of general relativity, providing evidence for the black hole's existence long before it was visually captured in 2018. S2 made its closest approach to Sagittarius A, venturing within a mere 120 astronomical units of the event horizon. At this closest point, it traveled at a remarkable 3% of the speed of light. Furthermore, we've identified numerous smaller stellar mass black holes by observing the gravitational waves generated when they collide in September 2015. The LIGO gravitational wave detector recorded these waves, resulting from the merger of two black holes located 1.3 billion light-years away from Earth. These black holes, with masses of 29 and 36 times that of the Sun, combined in less than 1/10 of a second. Remarkably, during this collision, the peak power output surpassed that of all the stars in the observable universe by a factor of 50. By the time these ripples reached us, over a billion years later, they caused minute fluctuations in the measured distances along LIGO's 4-kilometer-long laser arms, akin to the diameter of a proton. This pattern precisely aligned with the predictions of general relativity. Subsequently, LIGO and its counterpart Virgo have identified numerous mergers between black holes. Together, these diverse observations conclusively confirm the reality of neutron stars and black holes. When experimental evidence validates theoretical ideas, science fiction becomes science. As we delve deeper into the mysteries of the cosmos, it's essential to recognize these once fantastical entities as integral parts of nature. We must strive to understand them within the framework of known laws, while remaining open to discovering new principles that exceed even our boldest expectations. Gravitational equilibrium in the black holes. Music. Imagining black holes symbolizes gravity's supreme victory over all forces. Gravity, perpetually attractive, holds all within its reach toward a central point. Why does our universe showcase structures like stars, star clusters, galaxies, and galaxy clusters, where gravity appears to be in control? The idea of gravitational equilibrium holds the key here. Across the vast expanse of the cosmos, various structures maintain a delicate balance between the pull of gravity and the opposing forces of pressure or particle movements. This equilibrium is crucial for the stability of everything we observe in the universe. Consider galaxies, for instance. Despite appearing to move away from each other due to cosmic expansion, their overall motion is tempered by the gravitational influence exerted by the combined mass and energy within the universe. This gravitational tug-of-war acts as a counterforce to the expansion, potentially even slowing it down or halting it altogether. The survival of structures hinges on maintaining this equilibrium. Should particle movements become too vigorous, a system risks disintegration, akin to the vast expansion that marked the Big Bang some 10 to 20 billion years ago. However, in cases where gravity overwhelms other forces, as in the formation of black holes, there's no turning back. The collapse is inevitable. Thus, the balance between gravitational pull and opposing forces determines the fate of celestial bodies and systems on a cosmic scale. In the realm of astronomical and cosmological studies, gravity holds sway over large-scale structures, dictating their behaviors. However, its influence dwindles significantly when we zoom into the atomic level. Consider an atom. when negatively charged electrons orbit a positively charged nucleus. Here, gravitational forces pale in comparison to the much stronger electrical forces, outmatched by a staggering 40 orders of magnitude. Even within a hydrogen molecule, comprising 2 protons and 2 electrons, gravity's effect is minuscule compared to electromagnetism. The gravitational pull between the protons is dwarfed by their electrical attraction, outmatched by a factor of 10 raised to the power of 36. At everyday scales, like those encountered in laboratories or with commonplace objects, gravity remains almost imperceptible. Whether it's a rock, a person, an asteroid, or even a small planet, the electromagnetic forces between atoms and molecules reign supreme over gravitational attraction. However, as objects grow larger, gravity gradually asserts itself. It significantly amplifies exponentially with mass. For each 1,000-fold increase in mass, gravity's relative importance surges 100-fold. What makes gravity influential, primarily on grand scales and objects visible to the naked eye, is that the positive and negative charges are distributed in nearly equal amounts, causing electrical forces to largely cancel each other out. However, gravity doesn't experience such balancing. Every object possesses the same gravitational charge, drawing everything toward it. Consequently, gravity emerges as the dominant force on sufficiently large scales. But how large is large enough? Only when dealing with masses comparable to those of planets does gravity start to contend with other forces. Take Jupiter, the largest planet in our solar system, for instance. Comprised of approximately 10 raised to the power of 54 atoms, about 1/1000th of the Sun's mass. Jupiter represents one of the most massive bodies, whose gravitational pull can be counteracted by the interatomic forces found in solids or liquids. Should a celestial body surpass Jupiter's mass significantly, gravity would exert such intense pressure that it would compress the body to an exceptionally high density. Consequently, a cold body much larger than Jupiter would paradoxically have a smaller radius due to gravitational compression. To grasp how black holes form by losing gravitational balance, we first need to understand how balance is maintained. Picture a satellite circling the Earth. It's constantly falling toward it, but its sideways speed keeps it from crashing into the surface. This sideways momentum lets it loop around the Earth continuously. Likewise, the movement of stars in a galaxy or atoms in a star prevents them from being pulled together by gravity into a single point. The Sun, a typical star, possesses a mass 1,000 times greater than Jupiter's. If it were cold, gravity would crush it into a density 1,000,000 times denser than a regular solid, transforming it into a white dwarf star. This white dwarf would be approximately the size of Earth, but 330,000 times more massive. However, the Sun isn't a white dwarf because its core temperature reaches about 15 million degrees Celsius, far hotter than its glowing surface. At these extreme temperatures, the atomic nuclei within the Sun move chaotically at speeds of hundreds of kilometers per second. It's the pressure generated by this intense heat and the swift motions of electrons and nuclei that counterbalance gravity's pull. In all Sun-like stars, stars within a galaxy can be likened to the atoms composing it in certain aspects. Galaxies are simpler than their individual stars. The vast distances between stars and a galaxy relative to their sizes make collisions unlikely. Therefore, their orbits can generally be traced independently. The primary force governing their movements is gravity alone, unlike within individual stars where various physical processes play crucial roles in their behavior. Our Milky Way galaxy alone contains an astounding 100 billion stars, and this is just one of the many galaxies scattered throughout the universe, all visible thanks to modern telescopes. The equilibrium within a galaxy is delicately maintained by a balancing act between gravity, which pulls stars inward, and the motion of stars, which, in the absence of gravity, would cause them to drift apart. Consider our Milky Way, a prime example of a disk galaxy. It features a flat platter of stars, all orbiting in nearly circular paths. The stars' movements within this disk are quite orderly and predictable. On the other hand, elliptical galaxies exhibit more haphazard star motions, with each star following a convoluted trajectory influenced by the gravitational pull of its neighbors. These elliptical galaxies often appear as large fuzzy spheres of stars, sometimes with flattened or irregular shapes. In addition to stars scattered throughout the galaxy, there are also several hundred globular clusters orbiting around the center of the Milky Way and similar galaxies. These clusters resemble miniature versions of elliptical galaxies, containing anywhere from 100,000 to a few million stars each, tracing their own unique path through space under the influence of gravity. To keep things from collapsing because of gravity, we need to understand how much they need to move. Let's imagine we could take apart the globular cluster 47 Tucani, star by star, and spread them out so far apart that their gravitational pull on each other becomes almost nothing. Breaking the cluster apart would require a significant amount of energy, just like the energy that holds it together. The energy needed to split something up depends on how its parts are spread out, not how we take it apart. When things move, like stars, they have a type of energy called kinetic energy, and this energy works against gravity's pull. In the Newtonian theory of gravity, which works well for objects moving much slower than light, the amount of kinetic energy needed to balance gravity is exactly the same as the gravitational energy. This means that if we added enough kinetic energy to the planets in the solar system, they could break free from the sun's gravitational pull. So, understanding how things move and the energy involved is crucial in preventing collapse due to gravity. The balance of energies within galaxies and clusters of galaxies is exactly the same. This fundamental principle is commonly known as the virial theorem. It also holds true for individual stars, including stars like the Sun. However, in the case of stars like the Sun, we refer to the moving energy as thermal energy. This term is used because the Sun's energy comes from the random movements of its atoms, which are influenced by temperature. In order for a system to maintain gravitational equilibrium, there must be a balance between the energy pulling objects together, which is gravitational binding energy, and the energy pushing against gravity from within, which is internal energy. This delicate balance ensures that galaxies, clusters of galaxies, and stars remain stable over time, resisting the pull of gravity to collapse inward. Gravitational balance can't last forever. To keep the Sun in balance, it needs a central power supply to replace the heat lost through its surface into space. The Sun has been shining for 4.5 billion years because of hydrogen turning into helium through fusion, but this power won't last forever. In about 5 billion years, the Sun's core will run out of hydrogen. Bigger stars, which shine brighter, have even shorter lifetimes. When a star runs low on energy, gravity squeezes its core even more. Another power source might kick in, like helium fusing into carbon and other elements higher up on the periodic table. But eventually, all the nuclear fuel will be used up. The Sun will cool down and become a white dwarf. Larger stars collapse even more, turning into stranger objects. Even systems made up of stars, such as globular clusters, can't maintain their balance forever. Over time, these clusters change gradually, and we can observe these changes by comparing clusters of different sizes and ages. Within a globular cluster, each star not only feels the overall gravitational pull from all the other stars, but also experiences discrete tugs from its neighboring stars. These interactions work to equalize the average speeds of stars throughout the cluster. However, rather than helping to preserve equilibrium, these interactions have the opposite effect. This is because the gravitational field weakens towards the outer regions of the cluster compared to the center. If all stars had similar speeds, some stars near the outer edge would be moving fast enough to escape the cluster's gravitational pull. Consequently, globular clusters and other stellar systems never truly achieve a permanent balance. They are constantly losing stars, gradually dissipating over time, as the fastest stars gradually depart from the outer edges of the cluster. The stars that remain on average possess less energy. This phenomenon, termed stellar evaporation, appears to exert a cooling influence on the cluster, akin to the cooling sensation experienced when water evaporates from the skin. Intuitively, we expect the random movements of stars within the cluster to decelerate as it undergoes evaporation, much like how a decrease in temperature typically correlates with reduced motion. However, the actual outcome defies this intuition. Instead of slowing down, the stars remaining within the cluster become more tightly bound together under the influence of gravity, resulting in an increase in their average speed. Thus, rather than cooling down as it loses energy, the cluster undergoes a counterintuitive heating process. This intriguing phenomenon underscores the intricate interplay between gravitational forces and the dynamics of stellar motion within a cluster. This unusual characteristic is a widespread trait of systems influenced by gravity. As they lose energy, they become hotter. For instance, if the sun were to lose its nuclear energy source, its core would gradually shrink as heat escapes. However, as the core contracts, it must generate even more heat to counteract the stronger gravitational force pulling inward. Similarly, within a star cluster, when stars evaporate from it, something comparable occurs. A closer examination of the structure of a star cluster reveals a rapid increase in the concentration of stars at its center. This phenomenon, termed the gravithermal catastrophe, was first proposed by Vio de Menon in 1962. It often leads to globular clusters possessing highly compact, tightly bound cores. This occurrence highlights a common tendency among gravitating systems to develop dense nuclei with exceptionally strong gravitational fields. Despite the counterintuitive nature of the process, most ideas about gravity, not just the one Einstein came up with, suggest that black holes can come into existence. They might have a few differences depending on the idea. People really want to find black holes because they're places where gravity is the strongest, so we can check if our ideas about gravity are right when things get really intense. But there are other reasons to look at black holes. Small ones, called stellar mass black holes, are interesting because they're like the leftovers of dead stars. They tell us what happens in the final parts of a star's life. It's surprising, but we can find them by looking for bright flickers of X-ray light. The huge black holes at the centers of galaxies might be like garbage dumps for galaxies. Or maybe they're the beginnings of galaxies forming in the early universe. Either way, the big bursts of energy they produce, like quasars and gas jets, are the most powerful things we know about in space. All these different things, from what Einstein said to those big gas jets, help us understand more about black holes. Black holes are like collapsed objects that have separated themselves from the rest of the universe. They leave behind a strong gravitational mark in the space they've vacated. Picture them having a boundary, like a one-way membrane. Stuff can fall in, but nothing, not even light, can get out. Even if the original object was complicated, a black hole's appearance from the outside is quite simple. The idea that complex processes can lead to such a neat outcome is fascinating to both astronomers and physicists. Physicists are especially interested because inside a black hole, there's a point called a singularity where normal gravity laws break down. Just like how we had to rethink things at the start of the 20th century with quantum theory, understanding black holes means extending our knowledge from general relativity to the quantum realm. So, black holes are right at the cutting edge of modern physics, with some saying the puzzles they pose are as profound as those that led to the development of quantum theory. The question of whether black holes exist and are accessible for study by astronomers is almost unanimously answered affirmatively by astrophysicists. It's evident that some massive stars end their lives, leaving behind black hole remnants, while many galaxies host supermassive black holes at their cores, containing millions of times the mass of our sun. Exploring how these black holes form and how they manifest themselves to us forms the basis of the story that unfolds. Music. Regular stars, such as our sun, are eternal. They maintain their stability through a delicate balance between gravity and the pressure generated by their hot interiors. Remove this pressure, and the sun would rapidly shrink in size, having its diameter reduced in under an hour. Conversely, if gravity were suddenly deactivated, the sun's hot interior would explosively disperse. Despite appearing as a constant presence in the sky for over 4 billion years, the sun's interior heat is gradually diminishing. The sunlight we bask in at the beach or in parks is a visible indication of this energy loss. Although nuclear reactions within the sun's core currently replenish this heat, they cannot persist indefinitely at their current pace. Eventually, like all stars, the sun will exhaust its nuclear fuel, leading to the breakdown of its delicate gravitational equilibrium. In the 19th century, it became evident that a central energy provider was essential to replenish the energy lost by a star. Without the central source, the sun would gradually diminish in size due to heat loss, a phenomenon initially quantified by Lord Kelvin. However, unlike a rapid free fall, this shrinkage would occur slowly because it takes a significant amount of time for energy to seep out of the sun's interior, around 10 million years. To be precise, Kelvin recognized that this time frame was much shorter than the estimates proposed by biologists and geologists regarding the Earth's and its inhabitants' ages. It was apparent that some internal energy source within the sun must prolong its existence, and Kelvin demonstrated that chemical energy alone would not suffice. The resolution to Kelvin's dilemma only emerged in the 1930s when the potential of nuclear fusion was acknowledged. The sun's core, with its scorching temperatures, facilitates the fusion of hydrogen into helium at just the right rate to compensate for losses. Moreover, the energy released from this process is substantial enough that the sun could continue to shine for billions of years with its ample hydrogen supply. What occurs once a star exhausts its nuclear fuel? This inquiry is not solely about the distant future. Stars similar in mass to the sun, but formed billions of years prior during the early stages of our Milky Way, have already will transform into a white dwarf, a slowly cooling ember roughly the size of Earth, and can persist in this state indefinitely. Conversely, stars of greater mass undergo further contraction, culminating in their demise as neutron stars or black holes. In this part, we delve into the mechanisms and rationales behind these terminal states, laying the groundwork for exploring the astonishing and unforeseen ways in which these apparently dormant remnants have made themselves known. Since the 1930s, significant strides have been made in comprehending the structures and life cycles of stars, especially those resembling the sun. These stars commence their existence by condensing under the influence of gravity from interstellar clouds. Initially, they undergo a gravitational contraction akin to Lord Kelvin's predictions until fusion ignites in the core. Once the central temperature reaches a critical threshold, the star transitions into the main sequence phase, which represents the most enduring stage in its life cycle. The main sequence phase persists until a substantial portion of the hydrogen in the core, approximately 10% of the star's total hydrogen, is consumed. Throughout this phase, the star's power output, size, and surface temperature are intricately linked to its mass and to each other. When you glance at the night sky, you can spot stars of different colors. Bright stars range from red to blue-white. These colors show the star's temperatures. Hotter stars look bluer, while cooler ones appear redder. This is because light color depends on its energy, and hotter stars have more energetic light. This simple idea puzzled scientists in the past, leading to important discoveries about light and energy. Bigger stars are not only hotter and larger, but they're also significantly brighter. As a result, they consume their fuel much faster than smaller stars. Despite starting with a larger fuel reservoir, for instance, stars similar to the sun have enough nuclear fuel to sustain their shine for around 10 billion years. However, a star with 20 times the mass of the sun, for example, is almost 10,000 times brighter, but lives only a few million years. In the first few million years of their existence, stars oddly become brighter as they consume their nuclear fuel. This peculiar behavior is tied to the phenomenon where gravitational systems heat up as they cool down, as we discussed when exploring the fate of a globular cluster. As nuclear fusion progresses within the sun's core, hydrogen is steadily converted into helium. However, as the fuel diminishes, the efficiency of nuclear energy production decreases, causing the core to contract due to its own gravitational force. This contraction intensifies the gravitational pull experienced by the atoms in the core, accelerating the remaining hydrogen atoms. As atomic movement accelerates, so does the rate of nuclear reactions, resulting in an increase in power output. However, since nuclear reactions can only persist as long as there is fuel available, this heightened luminosity cannot be sustained indefinitely. The sun's transformation won't be very noticeable for another 5 billion years. After that, it will expand dramatically, becoming a red giant star, potentially engulfing the Earth in the process. However, it's not simply dispersing. Deep within the expanded outer layers of the red giant sun, the nuclear fusion process at the core will have compressed to the size of Earth during its red giant phase, lasting nearly 1 billion years. The star will burn hydrogen in a shell surrounding the now helium core. Following this, a shorter stage will occur where helium itself is consumed. Finally, the star will settle into a quiet end as a white dwarf. The story of how stars change over time, as told by astrophysicists, is quite complex. Their theories explain that a star's journey is shaped by intricate chains of nuclear reactions, along with subtle aspects of radiation and gravity. But how do we know if these theories are correct? We can't perform experiments on stars. All we can do is observe them. Also, stars live much longer than astronomers do, so we only get a single snapshot of each star's life. However, we have billions of stars to observe, and by studying stars of different ages, we can test our ideas about how stars are born and grow. It's like looking at a forest and understanding the life cycle of a tree by observing it for just one day. As the British astronomer William Herschel said, it's almost like seeing the whole life cycle of a planet at once, rather than watching it grow over time. One fascinating place to study is the Great Nebula in Orion, where new stars and possibly new solar systems are forming within glowing clouds of gas. Astronomers can also test their theories by studying the groups of stars in globular clusters of up to 1 million stars held together by gravity. These clusters contain stars of various sizes that likely form around the same time, giving astronomers valuable insights into stellar evolution. The same stellar evolution will eventually transform our sun into a white dwarf star. In the next part of this video, we will explore these unique types of stars. But before we continue, I have a request. If you enjoyed the video or found it informative, please subscribe, like, and leave a comment. It's free for you, but it greatly supports our channel. Gravity does not always have the final say. The sun's eventual transformation into a white dwarf will ensure a stable fate. White dwarfs are a unique type of star that can maintain gravitational equilibrium indefinitely without requiring nuclear reactions or any other power source. Unlike ordinary stars, which are supported against gravitational collapse by thermal pressure, white dwarfs rely on the random motions of their constituent particles. These motions are independent of the gas temperature within the star. Consequently, as white dwarfs gradually radiate away their internal thermal energy and cool down over time, they do not lose the pressure support that keeps them from collapsing. This remarkable stability allows white dwarfs to remain intact and unchanged for billions of years. The pressure that supports a white dwarf is called degeneracy pressure. This pressure arises from a quantum effect known as the Pauli exclusion principle. According to this principle, two identical particles, such as protons, electrons, and neutrons, cannot share the same position and momentum. These particles are called fermions, named after physicist Enrico Fermi. Fermions have a unique property called spin, which is half a unit of quantum mechanical angular momentum. This spin prevents fermions from being packed too closely together. Essentially, no two fermions can be in the same place with the same velocity. When fermions are packed tightly, they can't all move slowly. Most must have high velocities. This high-speed movement creates a pressure that resists further compression, in addition to any pressure from their thermal energy. This quantum effect is crucial for the stability of white dwarfs. Even as they cool down and lose thermal energy, the degeneracy pressure remains, preventing them from collapsing. This allows white dwarfs to maintain their structure for billions of years, illustrating the fascinating interplay between quantum mechanics and stellar evolution. When most particle motion in a gas is due to quantum resistance to compression, the gas is called degenerate. This creates pressure that supports a star against collapse, like how thermal energy supports the sun. A star becomes a white dwarf when its electrons become degenerate, happening at a density about 1,000,000 times that of water. White dwarfs are about the size of Earth, but have a gravitational field 1,000,000 times stronger. There's a limit to how massive a white dwarf can be. As the white dwarf's mass increases, the random speed of its electrons also increases. For masses just above that of the Sun, these speeds approach the speed of light. In 1930, young theorist Subrahmanyan Chandrasekhar, known as Chandrasekhar, thought about this problem. He discovered that white dwarfs with masses over 1.4 times that of the Sun, known as the Chandrasekhar limit, can't stay stable at higher masses. Degeneracy pressure can't balance gravity, no matter how much the star is compressed. Chandrasekhar realized that if the electron speeds got close to the speed of light, the degenerate gas couldn't resist compression. A white dwarf above this limit would collapse under its own gravity in about a second. Chandrasekhar's discovery raised troubling questions. What happens to stars more massive than 1.4 times the Sun's mass when they run out of nuclear energy? Some thought that massive stars might lose most of their mass during their evolution and eventually become white dwarfs below the Chandrasekhar limit. We now know that massive stars shed a lot of mass through powerful stellar winds, so stars slightly more massive than 1.4 solar masses can end up as white dwarfs. However, stars much more massive than this cannot avoid the Chandrasekhar limit. Another possibility is that such a star could eject its outer layers in a supernova, leaving behind a neutron star. But there is also a mass limit for neutron stars, which is below 3 solar masses. If a star is too massive, it might undergo an unchecked collapse and become a black hole. And so, a mysterious puzzle emerged, igniting the quest that ultimately led to the thrilling discovery of the black hole mass gap theory. The black hole mass gap theory suggests there's a range of masses, around 2.5 to 5 times the Sun's mass, where we don't find many black holes. This gap might exist because it's hard for stars in this mass range to become black holes, or because these black holes are unstable. Before diving into the enigma of the black hole mass gap, let's first unravel the workings of massive stars and uncover the journey that leads them to their dramatic fate. The supernova. Stars heavier than the Sun go through a complex and dramatic evolution. Most eventually become white dwarfs, mainly made of carbon and oxygen. Inside these stars, the conditions never get hot enough to trigger nuclear fusion of carbon and oxygen into heavier elements. Nuclear reactions need the reacting particles to be very close together, but because of a quantum effect called tunneling, they don't need to be as close as we might think. However, protons and nuclei repel each other, trying to keep them apart. The heavier the nuclei, the stronger this repulsion. High velocity or temperature is needed to overcome this repulsion and start fusion reactions. As big stars get older, they use up fuel in a series of nuclear reactions, making heavier elements each time. This makes their core contract and heat up until new reactions can start. Our Sun will likely turn much of its core into carbon and oxygen before becoming a white dwarf. But for stars heavier than 5 to 8 times the Sun's mass, this process continues until iron forms. Creating heavier elements releases energy that stops the star from collapsing until it reaches iron, where no more energy can be released through nuclear reactions. Next comes one of astronomy's most spectacular events. A star, usually any star above 8 solar masses, forms an iron core heavier than 1.4 times the Sun's mass. This core is too massive to remain stable as a white dwarf. It surpasses Chandrasekhar's limit. Since iron can't undergo nuclear reactions to release energy, the fuel supply stops, leading to a sudden and catastrophic collapse. The core implodes to the density of an atomic nucleus in a fraction of a second, reaching a density about 1,000,000,000,000 times that of water. During this collapse, The nuclear reactions that built the iron core are reversed. Iron nuclei break apart into smaller pieces until only a soup of subatomic particles remains. When energy is released by a series of reactions reversing those reactions, it needs an equal amount of energy. Where does this energy come from? It comes from gravity. The core collapse releases energy equal to about 10 times the star's total energy output from nuclear burning in its lifetime. To explain it differently, gravity, not nuclear reactions, supplies most of the energy during a massive star's life, but this happens mostly in the last second before the star's end. When stars collapse, the density in their core becomes incredibly high. Protons and electrons fuse to form neutrons, which are neutral particles like protons, but without an electric charge. Usually, neutrons are stable only when they're part of atomic nuclei, but in the dense core, they're created in a different way. During this process, a lot of extra energy is released. About 90% of this energy is carried away by elusive particles called neutrinos, which hardly interact with normal matter and mostly pass through the star without causing damage. The remaining 10% triggers a powerful explosion that blows off the star's outer layers. These explosions, known as supernovae, are rare events, happening only once or twice per century in our galaxy. Supernovae are rare but bright explosions in space that can be seen from far away. By studying many supernovae in other galaxies, astronomers have learned how their brightness and spectra change over time. However, it's hard to observe them for long because they fade quickly. On February 23, 1987, astronomers got lucky when they discovered a nearby supernova called Supernova 1987A in a galaxy called the Large Magellanic Cloud. This was special because they had observed the star before it exploded. Although the star didn't fit the expected color, it matched the theory of a massive star collapsing. What made this discovery even more exciting was that 2 underground detectors in Japan and Italy picked up a burst of neutrinos from the collapsing star's core. These neutrinos traveled through space and reached Earth just before the explosion was seen with telescopes. Even though the neutrino data weren't analyzed until later, they provided valuable information about the supernova's inner workings. It might seem odd that the collapse of a star's inner core causes the outer part to explode violently. Understanding the details of supernova explosions has been challenging. Several factors seem to work together to eject the star's outer layers at high speeds. One factor is known as the core bounce mechanism. As the core collapses and reaches nuclear density, the degenerate neutrons become rigid, resisting further compression and causing a sudden increase in pressure that halts the collapse. However, the core collapses so rapidly that it overshoots slightly and bounces back. This bouncing core collides with the still falling outer layers, giving them a push and sending them outward. However, computer models suggest that this mechanism alone is not enough, and the shock wave driving the explosion stalls inside the outer layers. Another contributing factor is the large number of neutrinos emitted from the heart-bouncing core. Although neutrinos interact weakly with matter, their sheer quantity provides an extra push to the outer layers, reigniting the shock wave and causing the final expulsion of the envelope. Although we have a basic idea of how supernovae explode, we haven't yet been able to simulate one entirely on a computer. Early calculations assumed the star was perfectly spherical, but this was too simple. Supernova explosions are messy and chaotic, influenced by factors like asymmetries, uneven chemical composition, and rotation. Recently, supercomputers have advanced enough to handle some of these complexities, such as rotation and convection, but there's still much we don't understand. However, the study of supernova 1987A has boosted confidence among supernova theorists, indicating that they're likely on the right track. Supernova explosions scatter the same chemical elements found on Earth, but the leftover remnant is far from ordinary. About 60 years ago, astronomers Walter Baade and Fritz Zwicky proposed a bold idea. They suggested that a supernova transforms an ordinary star into a neutron star, made mostly of neutrons. They theorized that the explosion happens when the star's core collapses, releasing a burst of gravitational energy. What's left behind is a tiny object. The star squished to just 10 kilometers in size, with a density much higher than anything we encounter in everyday life, even higher than a white dwarf. Astronomers found that the seemingly ordinary star in the middle of the Crab Nebula was actually blinking rapidly, 30 times every second. Such quick blinking suggests it must be a neutron star, as nothing larger could spin so fast. Even a white dwarf would be too big for such speed. This discovery confirmed that pulsars are spinning neutron stars with powerful magnetic fields that emit beams of radiation, like lighthouse beams, visible each time they rotate. Since then, hundreds of pulsars have been found in our Milky Way galaxy, most formed in the last 100 million years, and are relatively close to us. Scientists estimate there could be at least 100 million neutron stars in our galaxy, nearly one for every supernova that's occurred. The discovery of a rapidly spinning pulsar helped solve why the Crab Nebula still shines brightly over 900 years after its explosion. Most nebulae, like the Orion Nebula, glow from shock gas and ultraviolet radiation from young stars. The blue glow in the nebula comes from scattered starlight, but the Crab Nebula's blue light is different. It's synchrotron radiation emitted by electrons or their antimatter counterparts, positrons, moving close to the speed of light in a magnetic field. These ultra-energetic particles radiate energy quickly, so they couldn't have retained it since the nebula formed in 1054. The spinning star acts as a particle accelerator, constantly producing fast electrons that create the blue light. The star's pulsing shows it's slowing down, but it's losing energy fast enough to keep the nebula glowing. Neutron stars are like extreme laboratories where we study matter under intense conditions. They're different from white dwarfs because they use neutron pressure to resist gravity. While we are not sure how heavy they can get, we think it's around 3 times the mass of the Sun. We can't dig into a neutron star, but we can learn a lot from pulsars, which are spinning neutron stars. Their precise timing tells us about what's going on inside. For example, when pulsars suddenly speed up, it suggests cracks in their outer layer, releasing stress. This tells us about the layers inside the star, like the solid crust and the fluid core. By studying these changes in spin, we're basically doing astrogeology, but in space. Inside a neutron star, you'd find layers similar to Earth, a crust, a liquid middle, and maybe a solid core. As you go deeper, you notice changes in composition. The outer crust is mostly iron, but deeper down you'd find exotic neutron-rich elements like nickel, germanium, and krypton arranged in a crystalline pattern. These elements are unstable in labs, but stable inside a neutron star due to the Pauli exclusion principle. Deeper still, the density increases to about 10 to the power of 4 g per cubic centimeter. Here, you'd mainly find free neutrons, behaving like a superfluid, similar to how helium behaves at very low temperatures. This fluid has unique properties, like no internal resistance, meaning a spinning vortex would last forever. Some protons and electrons remain, likely behaving like electrical superconductors with no electrical resistance in the core, where densities are even higher. Things get more uncertain. There might even be quark nuggets, which are bits of protons and neutrons condensed into a solid. Neutron stars are like supermagnets, but way stronger than anything on Earth. Their magnetic fields can be trillions of times stronger than Earth's. Just imagine the magnets on your fridge are billions of times weaker. These intense fields can stretch atoms into long shapes. Outside the neutron star, these magnetic fields create powerful beams of radio waves, like a lighthouse. They also act as a supercharged particle accelerator, making high-energy particles that keep the Crab Nebula glowing. The radiation from neutron stars is so intense it surpasses even the strongest lasers on Earth. In this extreme environment, the interaction between radiation and the magnetic field creates pairs of particles called electron-positron pairs, which produce the radiation we see. Neutron stars also have incredibly strong gravity. Climbing even a tiny bump on their surface would take more energy than escaping Earth's gravity altogether. Because of this intense gravity, Any structure on the surface would be squashed flat. It's so extreme that observing a neutron star would only be possible from a free-falling orbiting platform. But even then, the conditions would be tough due to tidal effects. A rocket would need to reach about half the speed of light to escape from a neutron star surface, compared to just 11 kilometers per second, or about 27,000 times slower, to escape Earth. The gravitational binding energy, which is the energy needed to break apart the star, is huge, about 10 to 20% of the total energy that could be released if all the star's matter were turned into energy, as in Einstein's famous equation. This immense energy comes from gravity. As a collapsing stellar core contracts, it spins faster, just like a skater spins faster by pulling in her arms. This faster rotation is due to the conservation of angular momentum. The gravitational force does work on the star, increasing its rotational energy. Similarly, a star's magnetic field can become incredibly strong as it collapses into a neutron star by a factor of over 10 billion. This is because magnetic field lines get squeezed. This increase in magnetic energy is also powered by gravity. So, gravity not only fuels the explosion of a supernova, but also leaves behind a dead star with more energy than nuclear reactions could produce over its entire lifetime. In essence, gravity is the ultimate source of energy for phenomena like the Crab Nebula's glow. Leaving the Crab Nebula, let's consider a historical what-if scenario. Although the nebula's central pulsar is visible through large optical telescopes, its pulse rate is so rapid that it appears as a continuous source of light to the human eye. However, if the pulsar had been spinning at a slower rate, say 10 times per second instead of 30, its unique characteristics could have been detected 60 years earlier, well before the advent of radio astronomy. Imagine if superdense matter had been identified in the 1920s, predating the discovery of neutrons on Earth. While we can only speculate, it's likely that the significance of astronomy for fundamental physics would have been recognized much earlier in the 20th century. It doesn't seem like stars actively try to avoid gravitational collapse. Throughout their evolution, stars can lose a significant amount of mass, with some stars up to 5 or even 8 times the mass of the Sun ending up as white dwarfs. However, the discovery of neutron stars and supernova remnants indicates that even heavier stars don't shed enough gas to reduce their mass below the Chandrasekhar limit. Neutron stars have an upper mass limit of 2 or 3 solar masses, which isn't much larger than the limit for white dwarfs. There are no theoretical arguments suggesting that stellar evolution should allow for the existence of remnants too massive to become white dwarfs, while preventing those that are too massive to become neutron stars. Hence, stellar remnants heavier than roughly 2 or 3 solar masses are destined to experience full gravitational collapse into black holes. This is because once their nuclear energy sources are depleted, no internal pressure can support them in equilibrium. While these collapsed entities may not be as abundant as neutron stars, there could still be millions of them in our galaxy. Certain types of supernovae could lead to the formation of black holes instead of neutron stars. Alternatively, some massive stars may collapse without generating any noticeable supernova-like blast. Where might these purported remnants of black holes be located? Can we detect them? While theoretical reasoning is informative to a degree, we require tangible proof before we can substitute speculation with certainty. Fortunately, the emergence of a novel form of observational astronomy in the 1960s, ray astronomy, directly yielded compelling evidence for stellar mass black holes in our nearby galactic vicinity. Next arrived the Event Horizon Telescope, a monumental milestone in the realm of black holes. An image captured by this array of telescopes validated all the conjectures that had unsettled physicists and astronomers. And thus, we have reached the conclusion of the initial segment of our series. Stay tuned for the next segment of our thrilling video series as we explore the mysteries of black holes in greater depth. Be ready for the launch of our upcoming video. And in the meantime, show your support by liking, commenting, and subscribing to our channel. Your engagement will truly elevate our content